Dion will be next. She's at the far end. She's the Director of Medical Operations Research Laboratory and an assistant professor at the University of Toronto. Her research uses optimization models to increase efficiency while minimizing potential harms in medical procedures and organ transplant and radiotherapy.
Okay, hi, I'm Professor Dion Aleman, like Mike. I'm a professor in the Department of Mechanical and Industrial Engineering, and I'm one of the faculty members associated with the Center for Research in Healthcare Engineering, and I specifically run the Medical Operations Research Lab, or MORE Lab. And I want to apologize in advance for the roughness of my slides. I had to make them about 5 minutes before the panel because Maggie told me that no one else had slides. So I'm sorry, Dawn, but I can't give her the best grade possible. I have to give her the worst grade possible. A minus minus. I'm just kidding. So I'm just going to talk a little bit about what is operations research, since it's in the title of my lab, and probably not everybody actually knows what that is. I know no one I know knows what it is, and when I say, oh yeah, I do research in operations research, people say, what is that? And I say, well, actually, more like what isn't operations research? So operations research is the branch of industrial engineering that looks at taking real-world problems, deconstructing them into a bunch of mathematical equations, and then doing something useful with those equations, like helping make optimal decisions. And this is the type of industrial engineering that you'll find in the most common applications of industrial engineering. When people think of IEs, they think of things like supply chain and logistics and vehicle routing. How do we help UPS and FedEx spend the least amount of money and the least amount of gas or the least amount of time getting all of their packages from some local distributors to all the different houses where they need to go. And more recently, you can find industrial engineering and optimization in financial engineering. Okay, things like how do you come up with the best combination of stocks to most closely model the stock market index? Although perhaps these days that's not the smartest idea. Or how do you try to maximize your revenue while minimizing your risk? And all sorts of very fine and fast, detailed financial maneuvers to help you do whatever it is you want to do with your money. And some people say that tricks like this are what caused the financial crashes a few years ago, but I'm not so sure. You can also find operations research in military problems. In fact, OR grew out of military logistics. How do you move the troops and all the things that troops need from one place to another efficiently? And you can even find optimization in more sophisticated applications, like how can you help fighter jets better target their desired payload delivery rather than missing by however many meters and causing undesirable results. But of course, we're here to talk about healthcare and a million solutions in healthcare. So I'm going to talk not necessarily about a lot of solutions, but about a lot of questions that people are using operations research to answer with respect to healthcare. So like Mike touched upon, operations research very naturally sort of fits into the resource allocation questions that exist in healthcare. For example, how can we shorten wait times, specifically by looking at resources like doctors, nurses, operating rooms, beds. How do we design our shifts in such a way to meet our demand? Okay, these very classically fit into the operations research traditional areas, like how do we figure out how much of product A do we make versus product B if we only have so many resources on hand? These are basically the same things. Once we break down the actual problem, once we start looking at equations, well, equations are just equations, and some things just very naturally lend themselves to OR. In the past, I'd say maybe less than 10 years, it's becoming more and more common to find mathematical models existing in medical treatment. So not just helping hospitals run better and faster and more smoothly, but actually helping doctors figure out what they should do with their patient. So coming down from the very broad, hospital operations level to looking at individual patients and how can we use math to help Mrs. Jones better predict when she might have an epileptic seizure, right? And we can use data mining patterns. So data mining is the study of finding patterns in large amounts of information. You can actually model it as a mathematical optimization problem. Right? If we have an epileptic patient and they have tons and tons of data about EEG information, this thing coming from this probe and this data coming from that probe, how can we look at this time series of data and say this person's going to have a seizure within the next 10 minutes. So if you're driving, you should pull over. If you're standing, you should lay down. Or if there's preventative medication available, now's the time to take it. So like, a lot of epileptic people may have those highly trained dogs that can sense when something's about to happen and they give the owner a signal. Well, not everybody can afford a dog because that comes with more than just the cost of the dog. But if there was a device available that could, beep or blink or give you some other indication, that would obviously help a lot of people. And there's a lot of researchers that are doing mathematical optimization to do this prediction. And some of the more sophisticated methods can tell not only when is a seizure imminent, but where in the brain, because seizures don't necessarily occur in everywhere. They might occur in the front or in the back or different sides, and that might be useful to for medical doctors to know what to do next. Okay. So another popular area is in liver transplantation. So a couple of topics in liver transplantation. So for example, let's say you needed a liver transplant. When should you get that transplant? Should you get it the very instant that your doctor tells you you need a transplant? And traditionally, people think yes, if clinicians think yes, as soon as we know this person needs a transplant, we're putting them on the transplant list, or if they have a family donor who can give them a liver, because actually you only need a piece of the liver, and when you transplant that in, it will actually grow pretty amazingly. If they have someone who can donate, we should do it right now. But some industrial engineers took a look at the problem and said, well, actually, let's take a step back. What are we really trying to do here? So we're trying to maximize the total amount of life that the person has left, okay, adjusted for quality of life, because we don't want a long life that's not high quality, or maybe only very short life that's very quality. We want everything. So if we think of a person's life as being comprised of the amount of time that they live in good quality before the treatment, plus the amount of time that they live in good quality after the transplant, well, now we just have to figure out how do we maximize the sum of those two lifespans. So suddenly we have a mathematical equation that we can optimize, and actually, as it turns out, what the results showed is that when you do have end-stage liver disease, you should actually wait until your disease has progressed through a couple of the different grades that exist, and then get your transplant. Okay. Then, of course, there's a whole other question of, well, when should you put yourself on the wait list if you know you're going to have to wait a certain amount of time? But that very same group actually then started looking into that next question. Well, when should you put yourself on the wait list, and why are the wait lists so long? And obviously the group is based on the U.S. In the U.S., as you can tell from the picture of the U.S. What they found is that the way the liver waitlist systems work in the U.S. is that there are these different organ procurement organizations, or OPOs, that are distributed basically regionally throughout the U.S. And so if you're in one of these regions and you decide to donate an organ, it goes to the OPO in that region, which then distributes their organs back within the region. So there's basically no cross delivery of organs. But how do you think these regions are designed? By mathematical optimization? By studying processes, by demands and arrivals of new organs in the system? No, it's all politics and money and whatever else. So what they started looking into was, can we come up with mathematically motivated regions that can better serve the population? And of course the answer is yes, or at least according to the mathematical models. Not that any of that actually got implemented, but it was an interesting question. So another topic, and this is something that I research a little bit, is say you do need that organ. Okay, how do you find someone who's a good match for you? Okay, let's say you have two siblings and they both say, "Oh, I'll give you my kidney," or "I'll give you a sample of my my bone marrow stem cells for your transplant." Well, how do you pick which one is better? Okay, well, who knows? The way things are done right now, there's not necessarily a lot of criteria that are looked at, because when you think about a person and all the information that we could possibly know about a person, it's just a tremendous amount of information. Like, a person has 33,000 genes. How are we going to look at all 33,000 genes of the donor and all 33,000 genes of the patient, plus things like matching age, exposure to different diseases in their life, and blood type, and yada yada? How are we going to make a match? It's really quite complicated, but again, it comes down to searching for patterns in data, which can be formulated as optimization problem. And it turns out that, in fact, we can figure out patterns from the data that says, well, if this is a kidney transplant and the donor has this property and the recipient has this property, then you should definitely not do that transplant. Or maybe that transplant is going to have an 80% success rate. Okay. Another optimization problem that some people are looking at is how to select paired exchanges. So let's say you have a group of 20 people who need kidney transplants, and they all have someone who's willing to donate a kidney for them, but maybe that partner that each person has isn't necessarily a good match for that person. Well, how can you basically arrange a big ring of like, well, you give me yours, and he'll give me his, and you'll give that to that person, and basically this big convoluted matching so that everybody gets the kidney that's best for him or her. All right, again, it's common sense, okay, but it's not necessarily easy to implement. It's just optimization. Okay, another question, when should you provide a medical treatment or a diagnostic screening? So for example, for breast cancer, which has been in the news recently for the changing guidelines as to how often women should be screened for breast cancer, well, the reason why there's a lot of controversy about it is that the screening process involves radiation, and radiation eventually causes cancer, so you don't want to screen too soon or too often, because, well, that could be bad for later. So how can you do an optimization to figure out the best time to start screening? And here's one of my primary areas of research. So let's say you have cancer, or let's say you need a bone marrow transplant. What you might have in addition is radiation therapy. So questions in radiation therapy are, where should we orient all the beams of radiation that are pointed at a person's body, and what distribution should we use for each beam? Again, optimization. How do we maximize the amount of dose of the tumor, minimize the amount of dose to, say, the spinal cord? And I think this is my last topic slide. So if there's a pandemic, let's say, H1N1, SARS, okay, these things are not terribly foreign, how can we predict where the disease is going to spread? And more importantly, how can we slow and stop it? Well, Mike presented a whole bunch of examples of computer simulation, and, well, we can use computer simulation to try to figure out how are people behaving, how are they communicating, how are they transmitting disease to each other, and then figure out how might that disease spread through, for example here, the GTA, and then once we know how that might spread, then we can use an optimization model to figure out what are the best public health policies, like who should we vaccinate and when and with what priority, to try to figure out what's the fastest way that we can stem the spread of disease given a finite amount of resources, for example, vaccines. All right, so the main thing takeaway is operations research. It's everywhere. It's not just boring things like logistics, but it's also fun things like healthcare. Whether it's a million innovations in healthcare, a million innovations in green, or just a million innovations, period, if you can put a mathematical equation to it, chances are operations research could be a useful tactic to solve your problem. Okay, thank you.